So firstly, thank you, Alex, for inviting me, or Ricardo for volunteering me to come along to this. My name is Gary Emmerton. I'm a solutions architect at AWS, and today I'm going to talk about IoT with a little bit of a sprinkling of cloud. When I started my career, which was in the late 80s, I started actually in electronics, and this is why IoT is actually quite relevant for me. And then I sort of accidentally got a job in IT after working in electronics for a few years, which is probably what a lot of IT people do. And I've been bluffing my way through a career in IT ever since. But now, today I'm going to talk about IoT, so hopefully you'll learn a bit about IT. Does anyone in the room know anything about IT? Have you worked with IoT? A little bit. Has anyone got a Raspberry Pi?
Yeah.
Okay, probably. So if you've got a Raspberry Pi, there's nothing stopping you from doing some IoT stuff. So, what I'd like to start with is a brief history of IoT, or it's less a history, more of some of the origins of IoT. And I like to think that, people say necessity is the mother of invention. I actually think it's either lazy devs or efficiency is the mother of invention. And this is, I think, demonstrated amply by IoT origins. So, if we look back to 1982, this is a Coke machine at Carnegie Mellon University. And apparently the people working at Carnegie Mellon University in this lab thought it was a lot of effort to go to the Coke machine and then deal with the disappointment that the Coke machine might be empty. So they started monitoring the Coke machine so that they knew if there was Coke there before they went to the machine. Now, looking at the Max sitting beside it wasn't really much of a long walk, so it seemed a little bit of overkill, but it was up to them. 1990, this gentleman, John Ronke, connected his toaster to the internet. Very brave man. I would never connect a toaster to anything other than electricity and stand by it and watch it whilst it toasted. But he managed to turn his toaster on and off using SNMP, Simple Network Management Protocol. So, brave man. And then 1991, this is Cambridge University monitoring a coffee pot. I get the feeling that was the regular picture because no one went to the coffee pot because it was empty and therefore no one filled it up. But you get the point. You can start to monitor things and connect things that are not traditionally associated with being connected and monitored to a network. And you'll hear me say thing a lot, and it makes sense why IoT, Internet of Things, because it's describing that really it could be anything that you connect and you start to do something with. So, maybe a quick check next. How do we define IoT today? This is not an industry definition, this is sort of the Gary rough definition of IoT. Fundamentally, we're talking about physical devices that connect, talk to each other over a network, bi-directional communication. Things with sensors, things that interact with the external world. And again, this comes back to sort of my electronic background. It's something that you can actually see and touch, which is a bit more difficult when you're working with cloud all the time. So that's the fundamental. And the interaction, the communication between these devices is an important thing because that's where actually the power and value of IoT comes into its own. Found some interesting statistics. This comes from the World Economic Forum. I'm not quite sure how old this is, so it's probably a couple of years back, saying 75% of IoT projects are actually focused on these 5 sustainability goals. So it's sort of a good thing. It's seen as a technology for good. And that covers things like energy efficiency in industry. And I guess given current energy prices, there's a big motivation to actually do something with that. Certainly industrial companies, power is probably their biggest cost, so anything they can save on that makes a big difference. Health systems, a lot of health equipment is IoT enabled, so you can monitor the status of the equipment and monitor the patients remotely. Clean energy, so solar farms, wind farms, tidal farms, things that are remote. Again, the ability to monitor and manage those remotely where it's not always easy to get someone out there and have someone sitting on top of a wind turbine all the time, managing it, that's where IoT comes in. Responsible consumption, reducing wastage, being able to measure and manage things helps you reduce the amount of wastage that you get out of it. And then finally, smart cities, which is a bit of an amorphous term, where a lot of these things sort of come together, trying to make cities work better for their citizens. Now, some of the numbers that they came up with this, that IoT capabilities in this area will contribute something like between $4 and $11.5 trillion by 2025. Now that's about 14-15% of current world GDP. Not my numbers. Whether it comes to pass, I don't know. But the point is that IoT is a big area of technology and it's growing all the time. Click. So what actually goes to make up an IoT solution? I've pulled out what I consider to be some of the key components. This is not an exhaustive list. By doing all these things, you're not necessarily going to have a great IoT solution, but there's some of the key components that are worth understanding. So we've obviously got sensors, temperature, flow sensors, pressure sensors, accelerometers, anything that interacts with the physical environment. Microcontrollers. Something I didn't mention in sort of the statement, that these are physical devices, but they tend to be low power devices. You still need to have some kind of processing capability with them. So microcontrollers, microprocessors fits this bill perfectly because they're small, they have a certain amount of processing power, but they're low power consumption, but they can do just enough. Microcontrollers need to run operating systems still, so real-time operating systems, very different to a Windows, Linux, OS, a very small operating system which is focused on real-time actions on a single core processor. Does a lot of time slicing to make it appear like it's running loads of stuff at once, but it's not, it's just doing some good time slicing. Security, top of the list for pretty much every IT solution these days. Certificates is fundamental to security within IoT systems. If you're talking about hundreds, thousands, potentially millions, maybe billions one day, of systems that are out there that need to be secure, and you need them to authenticate and authorize against a central system, you don't want to be sticking usernames and passwords on those devices. So certificates gives you that option, or gives you that capability to manage the security for those devices. These two areas in here, protocol conversion and PLCs, this is sort of stepping into the world of industrial IoT. So where we're talking about managing manufacturing plants, factories, distribution warehouses, etc. A lot of these environments already have technology for controlling their manufacturing operations, for example. PLCs, programmable logic controllers, manage a lot of that operational capability. If you want to connect these things into PLCs, into your IoT ecosystem, then you need to do some protocol transformation and conversion. PLCs don't run TCP/IP. Modbus, OPC UA are traditional protocols that PLCs use. So if you want to have them working with an IoT ecosystem, which makes a lot of sense because they've got a lot of data, then protocol conversion is needed. The message broker side, I'm going to spend a bit of time on this in the next couple of slides because it's probably one of the most important bits to understand how IoT works, because I've talked about how devices communicate with each other, and central to that is a message broker, so I'll talk about that. And then finally we've got industrial PCs or edge gateways. So in a situation where, right, you've got your microcontroller but it's very limited, you need to do something with a bit more grunt, and that's where your edge gateway or your industrial PC comes in, something with a bit more processing power to do some of those heavier duty tasks within this kind of environment. Any questions so far on what I've said? Does this make sense? Roughly? Good, okay. So we'll move on. What I want to talk about next is messaging, because as I said, this is fundamental to IoT. So if we take a situation where we've got our temperature sensor and our microcontroller on the left hand side sitting out somewhere on our factory floor, we've already got our certificate on there, so it can authenticate and authorise itself to our message broker, our MQTT message broker. MQTT, by the way, stands for Message Queuing Telemetry Transport, just in case you're wondering. And then we have clients on this side. These clients are, if you like, applications or systems that are going to do something useful with the data that's coming out of this sensor. Now, MQTT works on a publisher-subscriber model. It's a very efficient, low overhead protocol, so it's perfect for environments where you need to send small messages, you need to send them frequently, and you need to be able to allow for potential, we say, dodgy network connections where it's not going to be reliable necessarily. So the publisher subscriber method works by our MQTT clients subscribing to a topic, and I'll speak more about topics in a second, to our message broker. And a topic is essentially a namespace on which messages are published. So they've subscribed to the message broker to that specific topic. Our temperature sensor then publishes a message, in this case its temperature reading, on that topic, and let's call that topic sensor 1, for example. It publishes that to the message broker. Because these are subscribed, they immediately get notified of that message, and then they can do something useful with that message, whether that is display on your mobile device that this is the temperature of your room or whatever, or do something useful with it, store it in a database, for example. So that's the fundamentals of how the messaging works, a publisher-subscriber model. And because this is using certificates as well, it's secure, so TLS encryption between all of the components. But fundamentally, these clients over here, they never talk directly to this system over here. You've got, effectively, you're decoupling them in the middle with the message broker. This is what an MQTT topic looks like. If you say that enough times, it really gets difficult. Their namespaces and they're hierarchical. So you specify these at runtime. So it's not like you've got to predefine a whole list of topics and things that you want to use. You can just send a message to a topic and call that topic whatever you want. It doesn't matter. So in this case, we've got your company name, a location, a part of that location, a piece of equipment within that location, and then in this case, a motor that is part of that piece of equipment. So in this case, the motor would be publishing, or the microcontroller attached to the motor will be publishing messages related to motor speed, motor load, current, etc. on that topic. Now, that's...
I do have a question.
Yes.
Is this format always the case? Is it always got to be the company and then that layer and that layer, or can it be?
It can be anything you like.
So it doesn't have to be. It could be, say, only like 4 levels.
It could be 1 level.
Okay.
You could just do motor 9. You could have, if you've got 5,000 motors, you could have 5,000 topics, or just call motor 1, 2, 3, 4, 5, 6, etc. Or you could just use factory. So this is completely free form. It just enables you to effectively say aggregate messages, but if I subscribe to a topic at this level, hash being a wildcard in MQTT, that's basically saying if I subscribe to that with an MQTT client, it's getting difficult, then I will get all of the messages from all of the conveyor belts, all of the motors sent to my client. So I could say level 1 conveyor C hash and get all the messages from those motors. So that's why the hierarchy works, because some people might want to see everything up to the whole factory level, so you can specify that how you like. Okay, so that's how the topic works. Now, the thing about IoT is, especially in industrial situations, is the last thing you want in your factory, if you lose your connection to the cloud or to your to your IoT backend, you don't want your factory to shut down and stop operating. You need your factory to continue to operate. So whilst we can have a cloud message broker, we can also have a local message broker. And this is where we can build some intelligence into our environment at the physical location. So in this case, we're talking about using an edge gateway. We can run a message broker on there. So in this situation, we've got our temperature sensor. Our temperature sensor can send its temperature over MQTT to our edge gateway. Our edge gateway can then, you can have components subscribed to that topic in the same way that these do over here, so that that code receives the temperature setting. And in this case, if the temperature is greater than or equal to 25, turn the fan on, cool things down, open, turn the pump on, open the valve, all those kind of things. So if you lose your connection to the cloud or to outside of that location, you've still got something that will work here and that can actually operate your machinery. This is still valid, but it doesn't stop the factory from working. Okay? And in the same way, as we've talked around sort of the publisher-subscriber model, the messages will eventually go up to the cloud as well. Right. Taking it one step further, this is where the protocol conversion piece comes in. So again, at the edge gateway, we can run protocol conversion. We can communicate with our PLC, which has its own programming language, which will run some logic for the machines it's connected to. But we can bring that into this environment, and we can make use of those messages, make use of the data, and send commands to it in the same way by running the protocol conversion. So that will just be a piece of software running on that edge gateway that does that for us. Okay. Now extending it to the cloud side of things. So I've talked a lot around the things we can do on the edge and the message broker. The power or the benefit of this really comes into its own when we think about how many devices and how many sensors are we going to be running over here. Any factory is going to be running, potentially thousands of motors, actuators, presses, and you might be running many thousands of those across a number of factories. So the volume of data, and we often talk about how you can, if you like, liberate your industrial data. In an industrial situation, you've got a ton of data, especially coming from existing equipment that people are not really making use of because they can't collect it at scale, they can't analyse it at scale. It's often too difficult to do. So by using this mechanism to get that data up into cloud, to then we have something called a rules engine. And a rules engine helps us act on the messages that we receive via the message broker. So in this case, what we're looking at is perhaps we want to send an alert to engineers. We want them to know that, right, our temperature has gone above 25 degrees, the fan's turned on, but the temperature keeps going up. So we can use the rules engine to say, well, it's not working, so we need to actually get an engineer out there. And we can do that based on conditions that we specify in here. At the same time, we can collect that data into a data store. Now, if you think about the kind of data we're going to get from here, what do you think is the primary dimension or type of data that we're going to get from these devices? What's the driving factor and commonality between any devices here? Anyone got any ideas?
Time.
Time, exactly. It's all time-driven data. You want to know temperature over time, you want to know water pressure over time, you want to know vibrations within a machine over time. So this data store traditionally should be a time series database. It makes it incredibly easy to then query over periods of time against that data and start to analyse it. Bring in things like machine learning. This is where it gives us that opportunity to start looking at things like predictive maintenance. How do you know when a machine is going to fail? How can you detect anomalies? Given the volume of data, this is actually very difficult for us poor human beings to be able to do. So use machine learning to predict when a machine is going to fail so that you can schedule in maintenance before it fails. I can't remember the actual numbers, but the cost of unscheduled maintenance compared to scheduled maintenance is an order of magnitude for a company that once they stop a factory, if it is unscheduled, they've got to stop all the other machines, whereas if it's scheduled, they can manage around that. They can redirect flows around the factory to cope with it. So the cost is significantly lower. And then analytics for us humans to see what's going on and to aggregate that data across large fleets of devices to look at energy efficiency across your entire factory setup, for example. So that's the messaging, and that's how we get all the data from these devices at scale into the cloud. Another final thing I wanted to cover is device shadows. So has anyone heard the term digital twin? Yeah. Digital twin's a bit of a buzzword at the moment, buzzwords at the moment. A device shadow is like an early version of that, and it's still relevant to being a digital twin. What it basically means is, in the same way we talk about message brokers and decoupling our devices from our applications, this gives us a digital representation of, in this case, our wind turbine in the cloud. And how this works is, our device publishes its current state. I'm spinning clockwise, for example. That then gets stored in JSON as a document against that shadow. What I can then do is with my application, I can request the current state of that device. Is it spinning? I'll get that from the shadow. I don't need to communicate with this end device, which is especially important if that link there is not necessarily persistent. I can then request a change of state. When this reports its state, it's the reported state. What I'm specifying here is I've got a desired state. I want it to, spin the other way. Probably a really bad example for a wind turbine, but let's say we're going to spin it the other way. So I can say I want that to happen. Because this is subscribed to its shadow, because it's underpinning MQTT, it immediately gets that state change, or when it establishes connectivity, if it's broken, and it starts spinning the other way. But at the moment, this app doesn't even know that's happened because it's not communicating directly with the device. So this now needs to report its current state again, and again, we get back to the application. So this is how we decouple that in a situation where you've got irregular communications. Okay. And finally, I've talked a lot about industrial IoT, but there's also consumer IoT. There are devices that, mobile devices, bad example, but if that was an IoT device, I'm carrying it around with me, it's not connected to a network. This is where we look at the different technologies that you can use to connect these mobile devices. LoRaWAN comes in to this place because it's cheap, it's low power, and it has good range for indoor and outdoor communications. So cellular, great, but as we know in Canterbury coverage isn't great, but it's a lot more expensive than using something like LoRaWAN. So that's how we can extend the connectivity to devices that aren't in physical locations out into the wild. Okay. Thank you. Hopefully that gave you a little bit of a taste. As I say, it's a broad subject, but hopefully I've covered sort of the key terminology and principles, and that made some sense at least. So thank you. Any questions?
Yeah, any questions?
Yes.
So I'm deploying some temperature humidity sensors at the moment in the hospital, and it uses an ISM banding. I've played about with, and so you were getting onto this was with your last slide.
Yeah.
I've dabbled about with Z-Wave. Is there kind of one communication protocol that is better than the rest?
No, it really depends on the environment, and that's the key thing where you can't say one size fits all. We're seeing like a lot from a factory perspective where it used to be Wi-Fi, they're now going to like private 5G type of connections because that works and it's less affected by machine noise. So yeah, it's about looking at the environment and figuring out what's the most effective communication means within that given environment. Okay.
You referenced JSON strings as a way of storing that data. At what point through from the sensor to that data store, where is that JSON created?
So
is it right down at the gateway, or is it further through?
the JSON object from a message perspective is effectively just the payload of the message. So when you create a publish a message to an MQTT topic,
Yeah.
you specify the payload as a JSON string.
Right
Yeah,
from there.
exactly. Yeah.
And if you were using an edge device in an industrial environment, would that be typically hardwired or Bluetooth or what?
Again, depending on the situation, if you look at things like PLCs and stuff like that, that will be hardwired. You traditionally have what's called an OT network, an operational technology network, which is separate from your IT network. So in a lot of cases that's existing. With new equipment going in, new sensors, again, depending on the environment, it can be obviously a lot easier to put in something that's wireless.
Yeah.
So you don't have to then route cable around an environment like that.
So it's quite a general question. What are the security implications for this, in your opinion?
The security is all about maintaining the integrity of the device at the end. So, for example, I mentioned it's certificate authentication. So maintaining the integrity of that certificate and being able to, and this is where we go into, there's a lot more to the security side, being able to detect when a certificate needs to be renewed, when it needs to be rotated, so that you can maintain the integrity, the security of that device. One of the biggest challenges is storing that certificate securely on the device, because if someone gets the device physically, then they potentially get the certificate. In an ideal world, you'll have some kind of hardware security, TPM module on the device which stores that certificate, but in a lot of cases that's just not possible. So it's about being able to detect early when there's a compromise and being able to revoke the certificate and renew it. And there's a whole load of automation that you can do around that, so it's not like a manual thing of trying to keep track of everything.
Okay, thank you.
Any other questions?
No.
Okay.
Thank you.
Thank you.